All right. Our next speaker is Professor Eric Mazumdar from Caltech, and he brings a very interesting perspective on looking at the mathematics of learning and mathematics in economics and such systems. And so he is actually interested in more of understanding more of the theoretical underpinnings of learning algorithms in this realm of uncertainty, dynamic environments that we're talking about here, and then applying them not just to kind of robotics but to online markets, healthcare, and large intelligent infrastructure projects. So welcome, Eric. We can get you started.
Now I can broadcast full screen. We'll share full screen. Okay, great. Thank you for the introduction. So today I'm going to be talking about kind of some recent work on independent learning with function approximation in competitive RL, or reinforcement learning. I should say this is the first time this is brand new work, so this is the first time I'm actually presenting it. So I'm very excited to hear your feedback. So I'm going to start with a really kind of 1,000-foot view of the problem, which is that we're increasingly interacting with learning algorithms kind of every single day, right? When we're ordering something on Uber, watching something on Netflix, or interacting with something on Amazon, I think this goes to show how these algorithms have actually been deployed across everyday life. But these algorithms, if they're actually used in the real world, are actually going to be used for basically consequential decision making. So, and making sure that we get this right is actually very important if we're going to use algorithms to, choose jail sentencing, use algorithms for basically planning airplanes on tarmacs, or even, actual self-driving applications. One of the biggest challenges that our algorithms face when they're actually used in the real world is actually just strategic decision-making on the part of people and other algorithms. So this is one of my kind of favorite toy examples, which is about how people respond to algorithmic decision-making in a very strategic way. This is a phenomenon known as Surge Club, which happens on Uber and Lyft and ride sharing, where Uber drivers will work together to basically manipulate the surge pricing algorithm. What they do is they'll go to a certain part of the city, turn off their app all at the same time to drive up the surge in that location. The surge pricing algorithm at Uber or Lyft will notice that it's lost a supply of drivers, surge the price there, and then the drivers will turn on their apps and collect the higher surge price. So to me, this is just a case of the complex strategic behaviors that algorithms have to deal with when they're actually deployed in the real world. And even superhuman AIs, or what we think of as these new class of superhuman AIs, are actually very susceptible to strategic decision making. So I think everyone here is very familiar with the successes of AlphaGo and reinforcement learning. In 2016, it beat the best human player. However, there's this kind of really interesting work that came out earlier this year where these folks, I think it was a combination of places, were able to kind of hand design policies that human amateurs could use consistently to beat the best Go playing bot 19 out of 20 times in competitive play. And this is a human amateur, not a human expert. There should normally be a video here, but I don't think it loaded. But what the actual policy looked like is that the person would distract the human bot in the top right corner and basically encircle them on the entire grid. It's a strategy that any person can kind of see happening. So a human expert would destroy very quickly, but these these Go bots just were not able to deal with. And so I could go on and on with these types of negative examples, but the reality is that these deployed learning algorithms are just going to be faced with strategic agents, and we need to basically build them with that in mind. So to me, I like to think about why these failures happen, and it's a lot of the time because the environments in which we train our algorithms looks a lot like this. We have a static environment. Our decision-making algorithm is taking in data and making decisions. But I don't think, I need to convince anyone in this room right now that learning in the real world or learning in the more complex systems looks a lot more like this picture, where we have decision-making algorithms that take in data and make decisions in uncertain dynamic environments that are evolving over time. And these algorithms are interacting not just with other algorithms, but also with other human decision makers. And so this is the goal of my work, is to try and kind of make some sense of this picture and design algorithms that can work in these kind of settings. And so today I'm going to talk to you about a very kind of specific project towards this, which is the convergence and function approximation in competitive reinforcement learning. And I should mention this is joint work primarily led by my postdoc Zai Chen at Caltech, but this is also joint work with Kaixing Zheng from Maryland, Asilas Douglar at MIT, and Adam Weirman also at Caltech. So the main question I'd like you to keep in mind is really, how can individual agents incorporate function approximation into their learning algorithms in these kind of dynamic environments while still having kind of performance and convergence guarantees. So I'm gonna, kind of start with a 1,000-foot view of learning in games, which is really just how should agents learn in dynamic game theoretic settings, right? These problems are a lot more complicated than the classic problems that people have studied in reinforcement learning, because the coupling between the learning agents make these problems, very non-stationary. It could lead to issues of non-convergence and everything. On the left there, I've actually shown a picture of what happens when players use policy gradient algorithms to play rock, paper, scissors. What happens is they actually end up evolving for all time on the surface of this torus in their joint strategy space. They never converge. They, on average, they end up doing the right thing, but it's not really very robust. So, this kind of makes me think about what makes good learning algorithms for game theoretic settings. What if we could, write down a checklist of the things that we want out of our learning algorithms, what would it be? So the first is that we'd like our algorithms to be convergent. We'd like them to converge in their last iterates or best iterates to some kind of equilibrium. The most common one is the Nash equilibrium. We'd like these algorithms to be independent, which means that agents shouldn't have to know anything about their environment. They shouldn't have to know anything about their payoffs. They should be able to learn about their payoffs through interaction with the environment. And so they shouldn't have to know anything about the opponent's utility function. And agents should be in some sense rational, right? They should be able to take advantage of naive opponents. But I think, and those three are pretty common in the literature on learning in games, but I think increasingly there's a big need for basically scalable algorithms for learning in games, because a lot of real world applications have extremely large state spaces, right? So, if you think of those self-driving car examples where they have to interact at an intersection or even go, the state space is massive. And that really leads us to think about incorporating function approximation into these problems. Great. So to start thinking about how we can design algorithms with all of these properties, I don't think we need to reinvent the wheel here, because we can already build on basically all of the work that's been done in single agent reinforcement learning and learning in games to kind of come up with these algorithms. So in particular, to address scalability, we know that there's a very good learning algorithm that works in very large state spaces in single agent settings. This is the kind of celebrated DQN paper, Deep Q Network paper from 2015, where they used function approximation, in particular deep neural networks, to play Atari games to great success. And this was really trying to address discursive dimensionality through the use of function approximation. On the other hand, to deal with strategic interactions, there's a huge number of kind of classical algorithms for learning in games that we could draw on. And in particular, today we're gonna draw on smooth fictitious play, which is this kind of classic learning algorithm. It's this generalization of fictitious play, which is one of the most common algorithms for learning in games. And it's an independent algorithm. It's convergent in finite action zero-sum games, and it's no regret. And basically what I'm going to show today is that under linear function approximation, DQN is rational, independent, and has finite time last iterate guarantees to Nash. Convergence guarantees to Nash in these two-player zero-sum Markov games. The main idea behind this result is that DQN, with a small caveat, can be viewed as smooth fictitious play under a basis transform. And so basically these two algorithms are in some sense equivalent. I say DQN star on the slide because we're going to make a tiny tweak to the classical DQN algorithm, which is really just to make it a 2-time scale algorithm to get the convergence properties to work. So the case that we're going to be looking at today is going to be zero-sum Markov games. So we're going to assume that both players have finite action spaces. We're going to assume that they have finite, but probably large state spaces. And we're going to assume that players only observe rewards and states. So they don't know anything about their opponent in these games. That kind of gets us back into this kind of payoff-based independent learning type of framework. So, a zero-sum Markov game is this setting where the two players will play actions into the environment. The environment will go to the next state depending on the two actions. And then the players will get rewards. One who gets a reward, the other one gets the negative of that reward. So it's a zero-sum game. And just for some notation, we're just going to denote the utilities of both players as depending on the policies of both players as U1 and U2, where U1 is the negative U2. So, just a comment, this generalizes obviously single agent RL and repeated matrix games. So we're hardly the first to, look at these types of games. Like, in fact, it has a really long history going back to the 1950s. And much more recently, there's been a huge amount of excitement around these areas by trying to bring in ideas of function approximation and kind of newer ideas in reinforcement learning. But so far, as far as I can tell, all of the works have been missing at least one of the following. They either don't have convergence on Markov games. They might not be payoff based, so they might use some information about their opponents. Most of them don't use function approximation, and very few of them have actually convergence in their last iterates. So before we dive in, I want to just have a little side note about smooth fictitious play, because I think it'll introduce a lot of the notation and the intuition that we'll build on for DQN. So smooth fictitious play is this generalization of fictitious play, where the idea is that players approximately will best respond to their opponent's empirical history of play. So at a given round, what happens is that players will compute their strategy as their smooth best response. And so it's smooth because of this entropy regularization. They'll play an action into the environment. They'll observe the action of their opponents, and they're going to update their belief over their opponent's empirical history of play. And this will repeat over and over again. Importantly, smooth fictitious play requires that you know your payoffs, right? Which is not really realistic in multi-agent reinforcement learning. And it requires observation of your opponent's actions. So suppose that you don't know your payoffs, you don't know your reward matrix A, and you can't observe your opponent's actions. So how should you basically learn an estimate of this term A pi 2 using only your own payoffs? So in zero-sum games, it's kind of easy. What we could do is just use stochastic approximation or TD learning on A pi 2 minus Q on this kind of fixed point here. And so this gets us into this kind of framework of smooth fictitious play, which uses bandit feedback, where around T, what you do is you play your action to the environment, you observe now your reward, you update your belief over your marginalized payoffs, and you smoothly best respond to that, and then you smoothly update your strategy. So the idea is you're going to use bandit feedback. You're doing TD learning on a fast time scale to estimate your marginalized payoffs. And then you're going to update your policy on that slower time scale so that on the slow time scale, it looks like you're doing smooth fictitious play. So in some prior work, we actually showed this algorithm has last iterate convergence guarantees in these kind of bandit feedback matrix games and also in Markov games. But one problem and I should point out that this algorithm is independent and payoff based, but it doesn't generalize to Markov games, and there's definitely no function approximation so far. So, I'm going to move now from matrix to Markov games, and I just wanted to really highlight the main differences here. On the left, I've written out the optimal Bellman recursion for the Q value in classic Q learning. On the right, it's basically the optimal recursion for Q learning in zero-sum games, where again, if we look at the only difference in those two equations is really that the expectation is taken over the actions of your opponent, right? And so just like in the single agent setting, the optimal Q function in a zero-sum game is a fixed point of a contraction mapping. But the problem now is that your contraction mapping depends on your opponent. Now, suppose that we have specified a function class, which is parameterized by weights. Then basically what we can do is this is the DQN algorithm up here. At round T, you play an action according to your policy. You observe your reward and move to a new state. Given all that information, you're going to update your belief. And in DQN, the way you update your belief, instead of doing basically a fixed point iteration, you update your weights via stochastic gradient descent on basically the squared difference. Given that, what you're going to do is update your policy, right? You're going to update your policy parameters, and then you're going to take a softmax for your policy, right? And then every case steps, you synchronize the policy and the weights. And so this is basically exactly the pseudocode of the DQN algorithm. The only difference really is that we've separated the timescales of the belief update and the strategy update. And if they were basically the same, then we'd recover DQN. Great. So I just want to highlight the relationship with smooth fictitious play that I spent so long talking about. So just for some intuition, suppose we're in a stateless regime and there's no discounting, right? Then, let's also assume all the fast timescales have converged. Then the DQN update looks like these terms on the left here. So you're going to basically do a smooth best response to your opponent's Q function, and then you're going to update your Q function in this kind of, again, this smooth way. And smooth best response on the right looks kind of exactly like I described it. You're going to build you have your marginalized payoff to your opponent's policy, and you're just going to smoothly best respond to it. So if you can kind of squint at these two sets of algorithms, you should kind of see that they look very similar. And if we do a kind of basis transform, you'll see that they actually become exactly the same. And this is basically the intuition for how we can prove the following result, which is that if we look at the Nash gap, or basically this Lyapunov function that characterizes the distance from the Nash equilibrium of this zero-sum game, and if we suppose that there exists a pair of policies such that the induced Markov chain is kind of irreducible and ergodic, then this DQN star algorithm in this zero-sum game has this kind of convergence guarantee here. So in particular, it converges in its last iterate sense. And it has this component here that depends on the kind of convergence of the min-max value iteration. This term here that depends on the convergence of that stochastic gradient descent algorithm. And then it has this term here that, that is the error that you get from a soft max policy. And then you get this last error term, which is really capturing how bad your function approximation error is. So how bad your neural net class might be at optimizing, or your linear function approximation class is at approximating the space of Q functions. So I should point out this is the first kind of independent payoff-based algorithm that provably incorporates function approximation in zero-sum Markov games. What's nice is this is really just a classic algorithm that a lot of practitioners are already familiar with, because it's something that they've been using basically already to solve games. And we just show that if they basically make a very small tweak and they just do it on 2 timescales, it actually has provable guarantees of convergence. So the proof sketch of this theorem is actually, as you can imagine, quite involved to show, because it's actually a finite sample rate. But the idea is we analyze the algorithm under the change of basis. So we basically analyze smooth fictitious play. And then we use this idea from kind of convex geometry, which is to analyze a smooth version of a Lyapunov function called a generalized Moreau envelope of kind of this Nash gap. And then we make use of the timescale separation to really deal with the time inhomogeneous Markovian noise that shows up because of the other players also changing their policies. Great. So kind of that brings me to the end of my talk. The takeaways are really that really small modifications to DQN allow it to have provable convergence guarantees in zero-sum Markov games. And I think there's a lot of kind of very exciting future directions that we can kind of build on, including getting this to work in other types of games, really thinking about efficiency. We know there's nothing optimal in the rate that I proved. It's just a proof that it does converge. Ideas of variance reduction, and really kind of building in all the heuristics that people often use in practice to show that how to do this in an optimal and efficient way. So with that, I just want to, say that this is all kind of at a very exciting intersection of economics, statistics, and optimization and control and algorithms. And these are really the types of problems that we have to do to address these issues of learning and decision making in societal systems. So with that, yeah, I'm happy to take any questions. Thanks for listening. Yep. Sure. I remember you talk about linear programming. Yep. Oh yeah, I guess this was in a revised part of version of the talk. So this is a slightly older one. Basically, when we say linear function approximation, I forgot to put it here. The QWs are linear functions of W's. Yeah, that's a good catch. Thank you very much. Have you ever tried to apply this algorithm to the continuous state space or continuous time space? Yeah, that's a very good question. Yeah, that's a very good question. So we haven't tried continuous action, continuous state spaces. We're currently running a lot of numerical experiments to validate this, and much larger in these kind of larger games where function approximation is necessary. But we haven't really tried to continue. But it's a obviously very cool application area. Thanks. Yep. What might have to be adapted if we went from away from zero sum? Yeah, that's a very good question. So the nice thing about zero sum games essentially is that we know that smooth fictitious play converges in zero sum games. So I mean, my guess is this will basically go very easily into potential games as well, because it'll converge in potential games. Beyond that, we don't have too many guarantees of when smooth fictitious play converges. It's a no regret algorithm. So we could say something about convergence to, CCEs and things like this. When no regret converges to Nash, maybe you could extend it. But unfortunately, since it's based around smooth fictitious play, it's a little bit hard to say anything in more generality than that. But if we could, it would be, obviously very cool. Thanks. Awesome. Thank you very much. Great talk.